So we just talked about the fault tree analysis, and we kind of focused on the qualitative fault tree analysis. Now, during the later stages of your life cycle, you'll have enough information so you can actually start filling in some of the failure probabilities, failure rates inside your fault tree. And then you can actually start verifying if your design truly meets your safety requirements. So we're going to talk about that quantitative fault tree analysis first, and then we're going to look at a couple other tools that are used too, like the data dependency diagrams and the Markov analysis. So basically, if you look at the AND gate that we saw in the fault tree analysis and the OR gate, you can actually relate the probabilities of failure, the event probabilities for A and B. You can then relate those to the top level events probability. So you know that probably if the probability of A is A, B is PB, then of course multiplying them together will give you the probability that A happened and B happened. In terms of an OR gate, if you have a probability of A and a probability of B, then the probability of that A happened or B happened is equal to probability that A happened plus the probability that B happened minus the probability that A and B happened at the same time. And the reason for that can be observed from the Venn diagram. You have the probability that A happens, the probability that B happens, and if you do that, of course, you count this little area over here twice, so you need to subtract it once. And this area is probability that A happened and B happened. Now you can extend the OR gate and the AND gate to 3 variables, and I have given that particular expression over there. Now, in some cases, 2 events A and B are mutually exclusive, and that happens that the probability that A and B happens at the same time is equal to 0. In that case, of course, PA plus B is equal to PA plus PB. Often we assume this mutual exclusion, but you have to be careful. Well, let's take a little example. Suppose the probability that A happens is 10 to the minus 2. The probability that B happens is 10 to the minus 3. So the probability that A or B happened is 10 to the minus 2 plus 10 to the minus 3 minus 10 to the minus 2 times 10 to the minus 3 is 10 to the minus 5. So you see that this is small compared to 10 to the minus 2 and 10 to the minus 3. So often it's ignored. Yeah? So because look at it, if you work it out, it becomes 0.01099. And if you compare it to just ignoring this end term, in other words, assuming it's mutually exclusive, then you see this is 0.011, which is of course the same as this if you round it up. Okay, so we already know that the probability of failure can definitely be related to the reliability. And we know that the probability of failure is really kind of the unreliability over a particular exposure time. Yeah, so then we know that Q, of course, is 1 minus RT. 1 minus the reliability is 1 minus e to the minus lambda t. And we saw before that for small values of the product lambda times t, smaller than 0.1 for example, Q would be equal to lambda t. In other words, also the probability of failure would be equal to the failure rate times the exposure time. Now, so if you look at the quantitative fault tree, really what we're trying to put in there is all these probabilities of failure. Now, you have to be a little bit beware of your parameters. Sometimes you see fault trees like the one you see in this picture, where on one end I use the probability of failure, but for these 2 events I'm actually using not the probability of failure, but I use a value of lambda and a value for t. Yeah? Now, of course, you know that lambda times t, that these 2 parameters together still determine the probability of failure. So even though I have different parameters here and there, since the product is equal to the probability of failure, you see that this kind of notation is used quite regularly. The nice part about this notation is that it splits the failure rate from the exposure time. So in this example, it's very helpful because you can see that besides seeing the failure rate of the individual components, you also see that the exposure times of these 2 events are different. Yeah. And then that way you can also introduce latent failures. And by latent failures, I mean failures that are already present in the system before you even start, for example, a flight. So in this case, I'm saying my flight time is 5 hours, but T1 is really the amount of time before the flight since you last checked item number 1. So it may have been broken already like 3 days before that you've started this flight. Another example are monitoring functions that are typically used to reduce the probability of failure, and this is just another example that you can take a peek at. Another thing to worry about fault tree analysis is independence. When you put together a qualitative fault tree, we really kind of try to make it as obvious in terms of logic. But if you start calculating a probability of failure of a top-level event, you need to take into account independence. For example, in this tree here, you see that the event A happens both in this particular subtree as well as in this particular subtree. So that means you have to be careful because you cannot take this probability of failure into account twice. So what do? We have to come up with the minimum cut set. So the way to do that is by taking the fault tree and writing it as a Boolean expression. So this case would be A plus B plus C and A plus D. In other words, there it is. Now you see that the term A occurs twice in this Boolean expression. So what we want to do is we want to minimize it and rewrite this expression such that each letter in this case only occurs once. So we do this by expanding the expression and minimizing the expression by realizing that A and A is of course equal to A, and A plus A times AD is A as well. We absorb the term AD into A. In other words, I'm making use of standard Boolean laws that you should still remember from digital logic. Yeah? Do you see A and A equals A? And there. Oops, there we go. Okay, so then finally you see this new expression only as each one of these letters, each one of these conditions, each one of these events only in there once. It's a minimum cut set. Now I can rewrite this again a little bit more efficient. Oh, sorry, it's a minimized Boolean expression. I can no longer reduce it. Of course, you see D happens twice here, but there's no way to get rid of D here because I could use none of the Boolean laws to reduce this expression. Yeah, so you minimize the Boolean expression. So it's different here. A absorbed the AD term. So in that case, I could get rid of the second A. Here, I cannot get rid of the second D. But of course, I can still rewrite it. I can still rewrite it as part to get rid of it. To only have it occur once is by taking D out, bring it outside the expression. So you get A plus B plus C times D. In that case, in your fault tree, A, B, C, and D only occur once. Now what I can do is I can put in my failure probabilities and go through the standard AND and OR logic. In other words, add the probabilities here, multiply them here, and add them here. Another example of a minimum cut set is this particular one here. Again, same things. I'm writing it out. So I have A plus B, B plus C plus D, and E plus F plus A times G, plus G, and H and J. So if you write it out, you get this top expression, and you can see by association that you can get rid of these little brackets. And then, of course, you can use the distribution law that we saw here to, make sure that really every letter only occurs once. At least that we have a minimized expression here. And of course, then you can rewrite the fault tree without anything happening twice. Again, be careful. We call this the minimum cut set, even though D happens twice. In this case, I made sure that we wrote the equation so that D only happens once, which clears things up so you can actually you only see the block once, so you wouldn't think or suspect that there is any dependence between multiple branches. Okay, so there's also, and I'm just going to touch upon this real quickly. I don't think it's that important unless you go into, of course, safety assessment professionally. In a lot of cases, you want to try to check out how important a particular event somewhere in the tree is with respect to the top level event. So, you know, which of the events in the fall tree would have the greatest impact on improvement of the top level event. And you see the fossil-Vesely importance factor, which looks at the probability of failure of the top level event minus the probability of failure of the top level event if you would fail X over the probability of the top level event. You see the relative change of the top level event with respect to the. Of course, the Birnbaum importance really means that you're going to just take the difference between when it works and it doesn't work. The second thing we're going to talk about are reliability block diagrams or data dependency diagrams. And in a sense, you're going to it's kind of another way of looking at the fault tree analysis. But they're a little easier to work with if you start talking about reliabilities. So what are we going to do? We take the fault tree analysis and replace the OR situations by series change and the AND situations by parallel change. For example, if you're saying that system 1 or system 2 or system 3 all the way to system N can fail, we talk about a series diagram. In this case, if each one has a reliability, then the overall system reliability of the series chain means it's just a product of the individual reliabilities. It's an OR gate, because remember, if any one of these systems fails, you cut the line so there is no longer a connection from the beginning to the end. You cut this line. That's also originally where the concept of minimum cut set comes from. And in one of the write-ups, in one of the Blackboard handouts, I talk about that. That talks about that a little bit. Well, if you do this and you replace this by exponential powers, you can also see that the overall failure rate of the series chain is the sum of the failure rates, and that really is easily explainable if you would replace each reliability by an exponential. On the other hand, you have parallel systems, and in parallel systems, what you're going to say is that in parallel systems, the unreliability of the parallel system is the product of the individual unreliabilities. And what you see here is that if now my system 1 breaks, there are still n-1 other paths that allow you to go from this spot to that spot. So that means the only time when you actually have no path from the input to the output is if all of them break. Hence, the overall system failure is the product on the individual system failures. So for example, for 2, you can actually say Q is equal to the product, and then you can express that again in terms of reliability. And you find out for 2 systems in parallel that would going to be equal to that the overall system reliability is the sum of the reliabilities minus the intersection. Now, if you have a little bit more complicated data dependency diagrams like this one, you can see, well, how can I simplify it and find the overall reliability of this system? I can just first say I'm going to take the bottom 2 and combine them. Well, you say they're in series, so they can be the reliability of B and C together is the product of their reliabilities. So now I have a new system on the bottom, BC, and a system on top, A, and these are in parallel. So now I can say, well, my overall system unreliability is the unreliability of A multiplied by the unreliability of BC. So I'm actually taking the unreliability by BC by actually taking 1 minus, of course, the system reliability, plugging this back into the unreliability equation and working it out. So now my whole system unreliability here is given by this equation. Another thing that you have to often worry about, or like another way of fault tolerance that's often introduced, is what I call standby systems. And for example, for for one standby component, you actually see it over here. So I have A works all the time, except for when it fails, the switch detects this failure and switches automatically to the B system. So the reliability of this standby system is really the reliability that no components fail until my exposure time, plus the reliability that one component fails until T. Yeah, because if one component fails, hey, we still have the other one left, and it would have switched over. So we typically, we have already identified this. This is just both of these are just Poisson distributions with an x equal to 0 for the top one, and x equal to 1 for the bottom one. So if you work it out, the reliability is just going to be e to minus lambda t, x equals 0, plus lambda t times e to minus lambda t. And then of course you can compare this to a standard parallel system, and you'll find out that the reliability is typically a little better for standby systems. Of course, one thing that you have to realize here, that we're assuming that the switch is perfect. Mean time between failure, remember, we're just going to integrate r, so from 0 to infinity. Okay, so if you want to take the standby system and actually implement it in the fault tree analysis, this diagram here shows you can do this actually by making use of a priority end. Now, of course, in the fault tree analysis, we saw that we had dependencies there, common cause failures. That's another name for those. And these common cause failures can also be present in data dependency or reliability block diagrams. For example, in this example I gave here, you see that A shows up both in the left subsystem as well as in the right part of this system. Now, what you can make use of is Bayes' rule. Bayes' rule says that if probability that X happens is the probability that X happens given Y happens times the probability that Y happens plus the probability that X happens given that Y doesn't happen times the probability that Y doesn't happen. Well, you say, well, that's mathematics. Let's look at the diagram. What are we going to do? So we're going to just consider two cases. We're going to consider a case in which we consider that A fails. In other words, A fails. And we consider the case that A works. And then we're just going to multiply these together. Yeah. So Px given Y is going to be, what does the block diagram look like if A does not fail? And RBD is when A does fail. Well, if A does not fail, that means this one works. That means that you can ignore it and make the connection from the input to that. So then this block diagram that you see here becomes much simpler. It becomes that 1 is in parallel to 2 and 3 is in parallel to 4. So first you're going to replace this system by 1 parallel to 2, then you replace this system 3 parallel to 4, and then you say, well, this system is in series to this system. And what you get, you're going to get this expression for the probability that X happens given Y. So the problem is that the system does not fail given that A does not fail. Yeah, the reliability. Now, if you want to have the probability that the system does not fail that while A does fail, now you need to say A fails. So you're cutting the bottom wire. That means that 2 is of no consequence. You're also cutting the bottom wire of this portion. That means 4 is of no consequence. So the system simply becomes 1 in series to 3. That means now the reliability is, or the probability that system does not fail, A does fails, given by the product of the reliabilities 1 and 3. Yeah. So how we combine it? Then we're going to combine it very simply. By saying, let me go back. I made a mistake here, of course. You're going to just assume that in this case, the probability that A does not fail is, of course, the reliability. I don't know why I call it D here, but this must be A, of course, but I'm just going to call it RD, so that's the reliability of component A. And in this case, it's the probability that A does fail, that's 1 minus the reliability of RD. So what you're going to take this, multiply it by that. and you're going to take this expression and multiply by that. So it means that you now have found via Bayes' rule the probability that the system does not fail, which is now, so in other words, the system reliability. Again, I'm sorry for the mistake. RD is really the reliability of A. I should have used an A there, I guess. Well, you can also do this with other weird systems like this one, for example. It's an example of what we refer to as a conditional system. And if you can see that this system works for taking a path 1, 5, 4, 2, 5, 3, 1, 3, 2, 4. So you see there's a variety of different combinations that make this system work. Yeah. Just to give you an idea what we typically do if you want to do a minimum cut set analysis, as given in one of the handouts that's given on Blackboard, you can just check out, okay, which ones do need to fail so we can actually not get from the input to the output. But let's actually look at just, what are you going to do? We can use Bayes again. We can say, first of all, okay, 5 works. Yeah, so then in that case it becomes just 1 in parallel to 2, 3 in parallel to 4. And the other case could be that 5 does not work, in which case this little line, this connection from that point to that point is broken. So this becomes 1 in series to 3, in parallel with 2 in series to 4. Yeah, so that's this expression here. Then of course you have to multiply this expression by the unreliability of component 5, and this expression by the reliability of component 5. So that's a way to deal with a little bit more complex systems, like conditional systems and systems with common cause failures. Now another one that I gave here, which comes directly from the fault tree handbook from NASA, which is also available on Blackboard, is this fuel system here that I break down and turn into a kind of reliability block diagram. You see I'm just taking all these components like the valve A and control valve B, and I'm turning it into blocks at each side.